So now we're going to introduce the concept of stoichiometry, and we're going to devote many lectures to talking about stoichiometry, which really is all about the quantitative mass relationships in chemical reactions. From a practical standpoint, you're going to be doing a lot of mathematics that are related to chemical reactions. So the first uh, topic under the broad umbrella of stoichiometry is to define atomic mass. We know what atomic mass is, right? It's the top number on the periodic table, the larger number associated with each element. And we talked about how atomic mass is the addition of the number of protons and the number of neutrons. But I want to talk now about what that number means. Atomic mass is a relative construct. And when I say relative, all of the atomic masses on the periodic table are relative to the atomic mass of the carbon 12 isotope. Now, the carbon 12 isotope was arbitrarily defined as having exactly 12 AMUs. An AMU is an atomic mass unit. So the arbitrary definition is that the carbon 12 isotope weighs 12 atomic mass units. Now, an atomic mass unit, or an AMU, is an infinitesimally small mass. It is approximately the mass of a hydrogen atom, which is approximately 1.66 times 10 to the minus 27 kilograms. Now, you know that a hydrogen atom really is just going to be about the mass of a proton. So this is approximately equal to the mass of a proton, which we also know is approximately equal to the mass of a neutron, just to give you an idea of what an atomic mass unit is. So now I want to look at the periodic table, and I want you to notice, this is something I've kind of drawn your attention to before, that the atomic masses on the periodic table, so these top numbers here, they're never whole numbers, right? They always have non-zero decimal places, and that's true for carbon as well. So the masses, the atomic masses on the periodic table are not whole numbers. And we talked about this when we first started talking about chemistry, but I want to draw your attention to why for our first stoichiometric calculation. Atomic masses are not whole numbers. Why? I'll give you a moment to think about why not. Well, we know that elements occur in nature as different isotopes, right? And they occur as a mixture of different isotopes. The atomic masses on the periodic table are kind of a weighted average of all of those naturally occurring isotopes, okay? So isotopes have different atomic masses. That's the definition of an isotope. Atoms of the same element with different numbers of neutrons, right? So isotopes are atoms of the same element with different atomic masses. The atomic masses on the periodic table are a weighted average. So the atomic masses that we see as the top number on the periodic table are a weighted average of those naturally occurring isotopes, where we have the mass of the isotopes, the mass of the individual isotopes that the element exists as, and then it's weighted by the percentage of their natural abundance. Okay, so you can say, okay, this element exists as, whatever percentage of this one isotope in nature. So let's do an example of that so you can see what I mean by this weighted average business. All right, indium is an element whose isotopes are mainly 2, okay? So indium isotopes occur naturally as 113 indium And that is only 4.2% of indium element in nature, and 115 indium. That heavier isotope represents the rest, 95.8% of natural indium. So, what is the average atomic mass of indium given those parameters? Okay, so notice that those percentages add up to 100. So these are the two major isotopes that indium can exist as. Before I can answer that question, I need to know exactly how much each of those isotopes weighs because it's not actually a whole number. So 113 indium has a mass that is exactly equal to 112.9043 atomic mass units. 115 indium has an exact mass of 114.9041 atomic mass units. So the masses are never quite equal to the whole numbers because of small differences in the mass of elementary particles, and that becomes kind of exaggerated with heavy elements like indium. So we need to do a weighted average, essentially. If we want to answer what the average atomic mass is of indium, we need to calculate a weighted average. And this is just like if you're trying to figure out what your grade in this class is going to be, you have to take your test average and multiply it by the percentage of how much the tests are worth, and then your homework average and multiply it by the percentage of how much the homeworks are worth, etc. So you're going to take the mass of the lighter isotope and then multiply it by the relative abundance, and then the mass of the heavier isotope, and then multiply it by its relative abundance to do a problem like this. So I'm going to take the light isotope mass, 112.9043 atomic mass units, and I'm going to multiply that by the relative abundance. I'm going to convert it to a decimal. That's the percentage. And to that, I'm going to add the mass of the heavier isotope, 114.9041 atomic mass units, and multiply that by its relative abundance, which is 95.8%. That gives me a weighted average of 114.82 atomic mass units. So this is the average atomic mass of indium, the weighted average, where the mass of each isotope is weighted by its relative abundance. Does this number match the number on the periodic table? So let's go back to the periodic table and find indium, and we will try to see if our number matches. Sure enough, 114.82 atomic mass units is the atomic mass of